Okay, back we go to it. So what we're going to do today is we're going to look at, I guess we're going to do operations with algebraic vectors. Yeah, so let's do that. So hope everyone is doing well. We're going to do operations with algebraic vectors. Alrighty. And I could write a date, but really, does it even matter anymore? Okay. So first things, how about we look at adding algebraic vectors? And we'll start with in R2. Okay, so adding two vectors in R2. So I'm going to just quickly sketch some basic axes, Cartesian plane stuff. Excuse me. And then say, all right, imagine we have the following vector. We've got this vector here. We're going to call it, what do I call it? Let's call this point up here. Right here. We'll call this point A. And I'm going to just arbitrarily say that A resides at the point x1, y1. Right? And then we're going to have a second vector. We'll do this color. And mysteriously, it's going to lead out to a point. Grab this, and then whatever it was, this. I'm going to call this point B. And point B is, of course, going to be at x2, y2. Okay. And so if I wanted to add these two vectors, so we're going to call these two vectors, I'm going to say we're going to add vector OA and vector OB. Okay, we're going to add those two. So OA plus OB is going to be equal to, well, it's going to be x1 plus x2 plus y1, not plus, excuse me, back up you, x1 plus x2, comma, y1 plus y2, which makes vector addition in algebraic terms dead easy, right? And so what does that look like? Well, the resultant vector, which is the name of the vector that when we take and we do an operation and what it yields, right? And so I can say, well, I really added OA plus OB. And so we go up here, and so up to that. Oh, I can't even tell. That's green. So let's make our resultant vector red. Red? Sure, red. So there's our resultant vector, right? That is the vector OA plus OB, right? And so that is our resultant vector. Now, you might say, oh, but what happens if we add it the other direction? Well, so there's this thing, and I think I mentioned it before, although I don't remember for sure, that's called the parallel law, the parallelogram law of addition. And it basically says that it doesn't really matter the order we add them in because we could add them in the other order, and it's going to take us to the same place, right? And so the parallelogram addition rules say we're going to still end up at this spot out here. And so this spot up here is, of course, OA plus OB. That's it right there. Okay. So it doesn't really matter the order we do it in. And so this is, beautifully extensible in R3, and I'm not going to draw a diagram of it, but in R3, if we were to take two vectors, if I said vector U, which was, of course, x1, y1, z1, and the vector v, which is going to be, as you can well imagine, x2, y2, z2, and we said what is u plus v? Well, it's going to simply be x1 plus x2, y1 plus y2, and z1 plus z2, right? And there it is. So beautifully extensible, easy peasy, nothing to it. Lovely. So there is addition of vectors in R2 and in R3. On we go. So did I label the first one 1? I don't remember. Yay me, I did. Okay, so then we're going to do subtraction of vectors in R2. So subtraction of vectors in R2. Okay, so again, we're going to look at this time, we're going to do OA minus OB. Okay, so sketching our axes again, just Cartesian axes again. There we go. And then, all right, so imagine that we had, here's my OA again. Oh, I need to go to bed. And then this one over here, do this as my OB. There it is. So I'm just going to go ahead and I'm going to label those. Do this and then make it thin again. Good. So I'm going to call this is A, and it's still going to be X1, Y1. And this is going to be B, and it's X2, Y2. Now, the order here clearly does matter because it's OA minus OB. Well, I have suggested that adding, and we're going to get to the algebra in a sec, certainly. Actually, let's look at the algebra first, and then we'll talk maybe about the geometry that goes along with this. And so it would be, of course, OA minus OB is simply going to be equal to x1 minus x2 and y1 minus y2. And so algebraic vectors are a thing of beauty when it comes to simple algebraic operations like this. Now, I had suggested that it is in our interest if we do it geometrically, that we never really want to subtract vectors. It's much easier to add vectors. So let's look at what we would do. So if we looked at this, from a geometric stance, it holds as well in algebraic, of course. But geometrically, I would say, well, instead of doing OA minus OB, I'm going to do OA plus negative OB. Well, negative OB is the same thing as, and I'm hoping you're thinking about it, is the same thing as BO. BO, get it? Anyway, that was not really planned. But that would mean that this vector is the same length as this vector, and it is parallel to that vector, or collinear when we talk about it in vector terms, but it would be in the opposite direction. So if I took, and again, because I have the luxury of having these tools, and I'm going to clone this guy. Why didn't you clone? Oh, why are you doing that? Stop that. Go back here. Clone. Oh, not the whole thing. Damn. All right, so this. Clone. All right, now I'm going to go up here, and I have this magical wizardry being able to go like that. So this vector here is the same vector, but in the opposite direction. And I get to add those together now. So if I added that, I don't really have much more room, that is what the result is going to be. And so the resultant vector here, because I'm going to go and I'm going to label this up here. So this is vector, really it's negative OB, and so maybe I'll, okay, so it's negative OB, also known as BO. And so the resultant vector is this one. Why are you not looking like a vector? Let's try. Yeah, okay, there it is. So there is the resultant vector. Okay, so this is the resultant. Okay, so geometrically that shows off. It's just lovely to be able to just simply do coordinate-wise subtraction like what we have over here. Lovely. And so then super extensible in R3. It is, of course, going to be x1 minus x2 and y1 minus y2 and z1 minus z2. Okay, easy peasy. Now, that's all well and good. No mysteries here. What happens when we get into something subtly different? So imagine that we had this case. So what about the vector, and I hinted at this earlier, that doesn't necessarily start or end at the origin. It goes from two random points. So what about the vector AB? Okay, well, that's an interesting one. So let's look at the diagram. The diagram definitely helps us sort this one out. So draw our Cartesian axes. And so imagine that we had this random point out here. So we had this point here, which we're going to call point A, which is going to be at the coordinates, unsurprisingly, x1 and y1. x1, y1. Okay. And then we've got another point out here, just another random point. Here's B. And you can predict that this is going to be x2, y2. But I want vector A, B. Okay, so vector A, B. The order of these letters matter, right? Vector AB is not equal to vector BA. They're the same magnitude and they are collinear, they're parallel, but they're opposite directions, so they're not the same thing. So where you place the head on this vector is important. So right now we're concerned with vector AB. So that means because this comes first, we start at A and we end at B, and that needs to be very clear from your diagram, right? So you have to make sure that it has the head pointed to the B. So now you might think, well, what's going on here? Well, I think that it's easiest if we have some numerics to go along with this. So imagine that I had actual ordered pairs here. So I'm going to go ahead and I'm going to ordered pair this up. So I'm going to say that imagine that A was, I don't know, what's that, like 3, 6. So imagine that A was at 3, 6, and B was at, if that's 6, that's going to be like 10 and about the same distance, 3. So 10 and 3. So B is at 10 and 3. Okay. And I want this vector. Well, it's the distance between these that's really, really important. So how much further to the right is B than A? So the distance, the x distance that we have covered, so vector AB in this case, you can see, oh, well, it's gone to the right 7 and it's gone down 3, so -3. And I think when we think about in terms of this, to go from 3 to 10, we've gone up 7. To go from 6 to 3, we've gone down 3. I think that's really, really, really logical. When we get into the more generic stuff like this, sometimes it's elusive to us. So I would encourage you that when you're working on these, sometimes you forget what the rules are. Put some actual ordered pairs on, solve it, and then use that to go back to the the more ephemeral, the more conceptual, not as physical manifestations of these things. So AB, I'm going to get rid of that chunk there because I don't need it anymore, is going to be equal to, there's my pen, is going to be equal to, well, it's going to be x2 minus x1, comma, y2 minus y1. Okay. Obvious right here, easy to forget here. You're like, oh, is it x1 minus x? Really, really easy to forget. And I will admit that I have a horrible memory. Every time, not every time, but frequently, I will draw this out, get that, and then be like, oh yeah, clearly it's x2 minus x1, right? And clearly it's y2 minus y1 to get those values. These values are very implicit, like you can just figure them out, no problem. These ones, it's easy to forget. Okay, so that's really, really important. It's x2 minus x1, y2 minus y1, or basically it is the heads point values minus the tails point values, right? So I'll even put that in there. It is the head minus the tail to get those values. However, I'd highly encourage for those of you that just don't have an ironclad memory that doing it like this is a really easy way. And so obviously it's very extensible. And in R3, what we're going to have is very similar. So if we had AB, it would of course be x2 minus x1, y2 minus y1, and z2 minus z1, right? So there it is. So super extensible. So again, I'm going to write underneath that. It's going to be, think about that as being head minus tail. Alternatively, I sometimes think about it as finish minus start, right? I'm going to take where I ended up and I'm going to subtract where I started from. But by all means, having an actual concrete example definitely simplifies and clarifies things in my mind, at least. Okay. All right, so some more groundwork type things. I'm going to grab a new page here so this isn't too long when I save it. Next thing I want to look at, what are we up to? 4? I think 4. Let's say 4. I'm going to look at vector magnitude of algebraic vectors. Okay, so we'll start in R2 again. Imagine that I said we have this vector. I'm going to call it vector OA. And OA is, we'll do a really easy one. So imagine that we did, it is at 6 and 8. Okay, so we've got this vector OA that's 6 and 8. I'm going to just draw that in really quickly. So vector 6, 8. So it's over 6. It's up 8. Here it is up here. Zoom. There's my vector. Why does it not have head on it? There it is. Okay, so there's my vector 6, 8. Maybe I'll label that point 6, 8. And so this is the vector OA. And imagine I said, hey, what is the magnitude of OA? Recall, of course, that the symbology for magnitude here is the absolute values. You place that inside the absolute values and it's saying, what is the magnitude? Meaning I want to know what the length of that vector is. Well, hopefully this kind of screams out at you as like, hey, we can do this pretty easily because what we have is of course, a right triangle. So I didn't choose those values randomly. They're nice values to use. The length of this leg on our right triangle is, of course, 6. The length of this leg is 8. And we can use Pythagorean theorem. So we can say, oh, well, that's going to be then the magnitude of OA squared is going to be equal to 6 squared plus 8 squared. And so that's going to be 36 plus 64, which is 100. And so that's the magnitude of OA. Oh, it should be OA like that. Squared, square root both sides. And we're going to find out then that the magnitude of OA is, of course, 10. Not plus or minus because we're going to have a negative length. So it's 10. Lovely. And so in general, right, if we are generalizing these things, we would say that the, given a vector OA with the coordinates x and then y, the magnitude of OA is equal to the root of x squared plus y squared. Okay, it's Pythagorean theorem. That's like, it is Pythagorean theorem. It's nothing more sophisticated than that. Lovely. Let's extend this into R3. In R3, so imagine we have another vector, OK, yeah, okay, yeah, and we're going to call OK. How about I don't know, like 1, 2, -8. And we think, all right, I want to know what is the magnitude of OK. Now, depending on who you had in grade 11 and or maybe even in grade 10, depending on your teacher, you might have explored the inner diagonals of like a rectangular prism, and you found the length of an inner diagonal of a rectangular prism. You might not have, but some of you might have. And so let's kind of envision what's going on here. So I'm going to go ahead. I'm going to just do a really quick sketch of this. Doesn't have to be super nice. And so we've got 1, 2, -8, way down here, right? Okay, so there's my vector. And what I want to know is I want to know what its magnitude is. Okay, and so I'm going to add some dimensions onto here with this. And then, nope, I want it to be thinner than that. It's thin, good. And then blue. All right, so 1 is out 1. So here it is right here, 1. And then it's over 2. So there's 2. And then down here is -8. And so, I would encourage you to, I'm going to just do a really garbage job, but I'm going to do a really quick parallelogram rectangular prism to go along with this. And I wasn't kidding about it being garbage. Did I do it right? I didn't do it right. Yeah, frig. Never mind. I'm not going to do that. I won't take the time to do that. So, nevertheless, we need to find its magnitude. Interesting thing about Pythagorean theorem, it extends into further dimensions. And so I'm just going to, say it. It is going to be equal to, in general, so let's do the general case, and then we'll do this exact case. If we had the magnitude of OA, it's going to be equal to the root of x squared plus y squared plus z squared. It's actually a really cool thing to prove, and then I like to do that, but I'm not going to dedicate the time. Just take it for granted that that's what it is. So it's going to be 1 squared plus 2 squared. In theory, you're going to say plus -8 squared, but I never do because it's going to be squared. So I'm just going to say 8 squared, but whatever. So that's going to be the root of 1 plus 4 plus 64, which is equal to the root of 69. Okay, so the magnitude of OK is going to be the root of 69. Okay, lovely. Pretty cool that it is just Pythagorean theorem extended. So it's probably that's a highlighter moment right now, that this is a formula that you're going to use. And I don't think you need to necessarily highlight that, because I'm sure shoot and hope that you understand that without me telling you that. But that's what it is. Okay, lovely. On we go. I don't want a highlighter anymore. I want a pen. Let's talk now about, what are we up to? 5, 6, 5. Unit vectors. Now, we said the key feature of a unit vector, and there's a couple, I guess, unit vectors, of course, they have a magnitude of 1. That is why it's called a unit vector, because it is 1 unit long. And the other thing that they have is they have a hat, not an arrow. Okay, so there are some really, really crucial and key, reserved word unit vectors, and that's what we're going to talk about right now. And so a unit vector that goes in the direction or is collinear to the x-axis is, so let's say that this is it right here, and it is 1 unit long. So if we added a point at the end of that, so imagine we had this little point right here, and the coordinates of that point would be 1, 0, 0. This has a special reserved name, this particular vector. This vector is not considered, it is named I hat. Okay, so it doesn't have the arrow as classic. It has the caret symbol over top, which denotes that this is a unit vector. Now, I hat is a particular unit vector. It is reserved. It is 1, 0, 0. It is the unit vector that is collinear to the x-axis towards the positive side. So it is 1, 0, 0. Clearly has a magnitude of 1, because if you take the 1 squared plus 0 squared plus 0 squared square rooted, you get 1. So it satisfies that it's a unit vector. And then let's then go over here and grab a red one. Along here. Again, if this was, a length of 1, that's probably not the right color, that the coordinates of this fella here are going to be 0, that's really big, 0, 1, 0, and it is J hat. And J hat is, again, a reserved code for the unit vector, which lays right upon the y-axis, and that's what we get. So it is 0, 1, 0. Lovely. And then we have another color here, that color. You can probably, whatever. You can predict that this is going to be 0, 0, 1, and it is, of course, K hat. Okay, so K hat is, of course, the unit vector along the z axis. So those are unit vectors. we talked about how to, I think we talked about how to find a unit vector in the same direction as another vector. And maybe I'll just revisit that again. So imagine, given the vector, how about 6, 1, -4? We'll call that vector OA again, let's say. So we had a vector OA. Imagine that I said determine a unit vector in the same direction, or better yet, collinear, in the same direction as OA, right? Well, that's the direction we want to go. So we were, if I were to graph that, so 6, 1, -4, and I want a unit vector. So, OA would go, sort of all the way down to here, but I want a vector that is 1 unit long that's in the same direction, right? So that means I would want some coordinates that would get me out to that spot. Well, it's not going to be 1, 0, 0 or 0, 1, 0. It deviates from the axes. Well, what we can do is we can say, all right, well, the unit vector, so OA hat, is going to be equal to the vector OA divided by its own magnitude, right? Because, if this vector was 10 units long, dividing it by 10 would shrink it down to be the size that we would need, right? So we would have to figure out what is the length or the magnitude of vector OA, and we could do that by saying, oh, that's going to be the root of 6 squared plus 1 squared plus 4 squared. And so that's 36, 37 plus 16 is 47, so 53, I think. You can point and laugh at me later if I got that wrong. So it's the root of 53. So if I wanted OA hat, I could write that in two different ways. I could say, oh, well, it's the vector OA divided by the root of 53, or, we have the coordinates of OA, so we could say it is 6, 1, and I think it was -4, wasn't it? 6, 1, -4, all divided by the root of 53. Alternatively, you could say, well, it's just straight up 6 over root 53, 1 over root 53, and -4 over the root of 53. Now, hopefully some of you are like, oh, that's bad form. It is bad form. I haven't rationalized the denominator. In post-secondary, some of your professors or your TAs will accept it like that, and others would be like, that's blasphemous. Don't leave it as with an unrationalized denominator. But you guys know how to do that. You multiply by root 53 over root 53. So for now, I'm going to say that I would accept that, but really it should be 6 root 53 over 53, because I've multiplied top and bottom by root 53, and then root 53 over 53, and then -4 root 53 over 53, and there it is, right? So that's the more elegant form, even though it looks pretty miserable, but there it is. So the other thing that's worth noting is any vector can be written in terms of the unit vectors I hat, j hat, k hat. Okay, and what I mean by that is that, given the vector OM is equal, that's a Scrabble word, by the way. OM is equal to, -4, 1, 5. You could say, oh, well, that means that it's actually -4 I hat plus 1 j hat plus 5 k hat, right? Because if I added those vectors, this is the result I would get back. Okay, so there we go. Lots of details. I will add the homework questions to Google Classroom. Have a lovely day.